Alright, welcome to our study video for Exam 1, Calc 3. Let's go ahead and get started. We're looking at some basic things to start off. How do you form the vector PQ if you're given points, and how do you get the length of the vector? So remember, we always subtract terminal minus initial. So head minus tail for each coordinate. So our vector PQ here is going to be 5 minus 4, which is 1, negative 1 minus 2, which is negative 3, and 1 minus negative 1, which is positive 2. And then PQ, length PQ, this is the sum of the squares of the coordinates and then take the square root. So square root of 1 squared plus negative 3 squared plus 2 squared. And if you do the arithmetic here, you get square root of 14. And we'd always prefer an exact answer there if we can get it. Up next, mix things up a little bit here. One vector's in component notation, the other is in IJK. And here we want a unit vector in the direction of u. So while that unit vector in the direction of u is just going to be given by u divided by its length. So remember that dividing by the length normalizes the vector down to length 1, and that's what we mean by unit vector. So we're going to take our vector u here. I'm going to write it in component notation. So that'd be 3 in the x-coordinate, is 0 in the y-coordinate, and negative 1 in the z. And then we're going to divide out the length. So square root of 3 squared plus 0 squared and negative 1 squared. So this is square root of 10 down in the denominator. We probably just write that as 1 over root 10 on the outside, scalar multiple, times the vector 3, 0, negative 1. So these point the same direction. This was our original vector u, except that this is length 1. The original vector was length square root of 10. Are the vectors parallel? U and V, are they parallel? Remember that two vectors are parallel only when they are multiples of each other. So if you compare these two vectors here, if we list the vector u, it is 3, 0, negative 1. And our vector v is 1, negative 2, positive 1. And they have to be multiples one way or another. Here I see if I multiply 1 by 3, I get 3. But to multiply negative 2 and get 0, I have to multiply by 0. So it's not a constant multiplier. So essentially what you're asking here is, can you get 3, 0, negative 1 to be a constant times 1, negative 2, 1, and it's got to be the same constant. And to work for the first coordinates, k would equal 3, but to work for the second coordinates, k equals 0. So they're not multiples. That's probably the easiest way to check. You should also know how to check when vectors are perpendicular. Remember that u would be perpendicular to v when the dot product is 0. So that's equivalent to u dot v equals 0. And then once you know one vector that's either perpendicular or parallel, then you know all of them, right? So all the vectors that are parallel to you are all these things that are multiples of 3, 0, negative 1. So in fact, right here, this is an expression for all the vectors that are parallel to 1, negative 2, 1. And so if you found a perpendicular vector, you could take any multiple of that vector. You get all possible perpendicular vectors. Okay, next we're going to project vector v onto vector u. So remember the picture here is you've got u here, and v looks like this. And you're going to perpendicular project v onto u. And the projection's right there. So this guy is right here. That's the projection. And remember, to get the projection, you do a scalar multiple of the vector u. And that multiple is, first you dot the vectors on top, and on the bottom you divide by the length of u squared. And then that's a scalar, and you multiply that times the vector u. So u dot v, let's go ahead and figure out the scalar that's up on top. So u dot v is going to be the dot product of these two guys. So you're going to dot 3, 0, negative 1 with 1, negative 2, 1. And then downstairs we want the length of u squared. Okay, well, we already found the length of u. Up here it's square root of 10. So on the bottom this is just root 10. And it gets squared. And that's our multiplier times the vector u, which is the 3, 0, negative 1. Whoops, not 7, 1. There we go. So this dot product, remember you multiply corresponding coordinates. So 3 times 1 is 3, 0 times negative 2 is 0, and 1 times, negative 1 times 1 is negative 1. And we add those guys up. So this is 3 plus 0 plus negative 1. And now we're dividing by 10. And we multiply that by our vector 3, 0, negative 1. So this is just what, 2/10, 1/5? So 1/5 times 3, 0, negative 1. Okay, and that is this vector right here. Okay, so there are a lot of other, types of, basic questions that I can ask here about vectors. So, if you want to check if two things are perpendicular, you check dot product. For parallel, you check multiples. If you want to find a vector that's perpendicular to two other vectors, you take the cross product. So all those sorts of general facts about vectors, that's kind of what I'm testing in this question. What's a projection of one vector onto another? What would be the, and notice that's the component of v in the direction of u. What would be the component perpendicular? So remember, what you do there is you take v and you subtract off this projection. So this guy over here, that's v minus the projection of v onto u. Okay, and that breaks v down into its components, the component parallel to v and the component perpendicular to v. Alright, now we're looking at equations of lines. We want both the vector and the parametric equations of a line that is perpendicular to this plane and passes through the point 1 to -2. So remember, for a line, we need a point and we need a direction vector. All right, well, we've got our point here. So this is our x0, y0, z0. And then we need our direction vector. All right, and we know this line is perpendicular to this plane. All right, well, that's got to give us the direction of the line here. So if we were to sketch a picture here, we've got this plane, and the line is perpendicular to that plane. Okay, so that line looks like this. And intersects at a point here, which may not be this point. Okay, that point 1, 2, let's see, that's a point on the line. That's not necessarily a point on the plane. That point 1, 2, -2 is on the line right there. And then what we know from the equation of the plane is we know a normal vector, n. And if both of those are perpendicular to the plane, then they've got to be parallel to each other. So we can take our direction vector v. V is going to be parallel to the normal vector. So they've got to be multiples of each other. Well, the easiest multiple to take is just to take v equals n. And remember, you can read the normal vector off here. -2, 3, -1. Okay, then that is our ABC. So vector equation of the line. That's our R of t is R0 plus t times v. R0 is this guy up here. So that's going to be 1, 2, -2. And then plus t times our direction vector, -2, 3, -1. And then if we want parametrics, we're just breaking it up into coordinates. So the x-coordinate 1 plus t times -2. So x would be equal to 1 minus 2t. Y-coordinate 2 t times 3. So that'd be 2 plus 3t. And your z-coordinate -2 t times -1. So z is going to be -2 and then minus t. And those are your parametrics. And then, of course, t varies over all real numbers. So there's lots of different ways that I can ask you to get an equation for a line. There's, you should look over the homework problems. But it all comes down to, getting that normal vector. In one case, we said, you're always given a point, but it's how to get that normal vector. So if it was parallel to another line, then they have to have the same normal vector. If it was perpendicular to another line, then the dot product of those vectors has to equal 0. So that tells you something about the vectors. If the line is, and here we had it was perpendicular to a plane. If the line was parallel to a plane, okay, so if you had the line down here, if it was parallel to the plane, that means that if you took the normal vector and the direction vector of the line and you dotted those, you would get 0. So there's lots of different conditions that could give you that direction vector. And I would recommend reviewing the homework problems here, and then even trying, maybe some other of the odd numbered homework problems in that section to give you some other ideas. And try to draw the pictures. Here we're finding an equation of a plane that contains some intersecting lines, and I give you vector equations of those lines. So let's draw a picture here. So remember, for a plane we need a point and a normal vector. And we've got two intersecting lines here. And they intersect at that point right there. And our normal vector here, what we can do is we can take the direction vectors of these two lines and take their cross product. So you'll have, a direction vector for the first line, we'll call that V1, and a direction vector here for the second line, call that V2. We can move those around so that the initial ends are at the point of intersection, and then the cross product of those two those two direction vectors is going to give your normal. So your normal here is going to be V1 cross V2, and then your plane contains both of these lines. So a couple of points right off that it contains are 0, 1, 4, and then also -1, 3, 4. So either one of those points is fine to use. Let's go ahead and use this first one. So let's let that be our x0, y0, z0. And let's go ahead and compute this cross product. So remember, you form a determinant with ijk in that first row. V1 goes in the second row, so that direction vector here's V1, and then right here is V2. So V1 here we're -1, 2, 0, and V2 is 1, -1, 1. And this will be positive I. And then we take out the row and column for I. We've got left 2, 0, -1, 1. And then minus. Minus goes with the j cofactor. Take out the row and the column for j. We've got -1, 0, 1, 1. And then plus k times our cofactor is going to be take out row and column for k, so -1, 2, 1, -1. And so this gives us 2 minus 0, so that's 2i minus -1 minus 0, so 2 minus -1j, 2i plus j. And then here we've got 1 minus 2, so that would be minus k. So our normal vector is just 2, 1, -1. Then we plug that into the scalar equation for a plane, which recall is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Normal vector is ABC, so that's our 2, our 1, and our -1. And then our x0, y0, z0 is up here, so it's going to be x minus 0 plus 1, y minus 1, and minus 1 times z minus 4, and equals 0. And then we can do some simplifying here if we want to. But actually on the exams I normally don't ask you to simplify because you're under a time pressure. So we could simplify this, but we have an equation. Now, if you would have used this point, that would have also been correct. And in fact, to get other points that are in that plane, you could take any value of t here, and because that'll give all the points on that line, that first line, any one of those points could be used here, here, and here as our x0, y0, z0. So there's infinitely many different answers at this stage, but they'll all simplify to the same equation. I'll give the same equation of the plane. And then this problem, just like the problems with lines, you've got to get a point and a normal vector. But there's lots of different ways that you could get that normal vector. So you'll want to look over the homework problems, and again, try some problems in the book, odd number problems there. Because remember, we had things like, okay, well, if you're given a point and then a line in the plane, then what you could do is you could find 2 points on that line, and then you could form two vectors like this and take the cross product of those two vectors to get your normal vector. Or if you're just given 3 points in the plane, that was the example that we did in the notes, then you form vectors like this and take the cross product. Or if you know a parallel plane, then the normal vectors are multiples of each other. If you know a perpendicular plane, then the dot product of the two vectors is 0. And that's going to give you information about the normal vector. So again, this isn't the end-all be-all. You need to do a little bit of extra work, but there will be an equation about lines and one equation about planes. But there's different varieties inside the same kind of question. Okay, next you're doing some matching, trying to match up some of the quadric surfaces and then cylindrical surfaces and some familiar surfaces with equations that you may have to do a little bit of manipulation with. So here you're going to have your quadric surfaces available to you. Okay, so you're just trying to look for general patterns in these. And we had some other surfaces, the cylindrical surfaces that we looked at, that were not quadric surfaces. So let's go back here and take a look. So here I see an x squared, a y squared, and a z squared. Everything's got positive terms. This 4y means that I'm going to have to complete the squares in the y. But still, I've got all positives and they're all squares. And then there's a 1 on the right-hand side. So my first thought is that this is going to be an ellipse. Or I'm sorry, an ellipsoid, which is choice D. And all we would have to do is just double check to make sure that the 1 doesn't go away when we complete the square on this. So if you did complete the square, you would factor out a 4 here, and you'd have it left in parentheses y squared plus y. And then you would take half of the middle term, which is 1/2, half of the middle term coefficient, which is 1/2. Squared is 1/4, so you do a plus 1/4 here, and that gets multiplied by a 4. So 4 times 1/4 is plus 1. So when you insert that 1/4 in there to complete the square, you're adding 1 to the left-hand side. So you would also add 1 to the right-hand side. So that means that this 1 doesn't go away. So then you'll have to divide both sides by 2. Okay, so you'll have some things in the denominator here when you put it in standard form. But the point is, this doesn't go down to a 0. So if we go back to our quadric surfaces here, it's going to look like this, except this is going to be y. Let's say it's going to be y plus 1/2 squared up on top. if we went to a 0 on the right hand side, then we'd be elliptic cone. So this has got to be an ellipsoid, which is D. Here I see two negatives on the left and a positive z squared. There's no shifting going on here, a 1 on the right hand side. So let's go and look at our forms here. So we had a 1 on the right hand side. This had two positives and a negative with a positive 1. This has two positives and a negative with a negative 1. Okay, so we need to multiply through by a negative 1 here. So positive, positive, negative, negative. Now in standard form we've got the negative 1 on the right hand side. So if we bring these coefficients downstairs, we are going to have a hyperboloid of 2 sheets there. So this is going to be E. And none of these guys gets used twice. Okay, next up, here we're solved for a y squared in terms of a positive x squared and a positive z squared. So go back and look over here. That's here we've got a z on the left hand side, here a z on the left hand side. Up here we've got a z squared on the left hand side. If a and b were 1, this would be z squared is x squared plus y squared. So this is going to this is an elliptic cone along the z. That means that this one's going to be an elliptic cone along the y. Okay, so that's going to be F. So in fact, elliptic cone, and it's along the y-axis. Just FYI. X squared plus y squared plus z squared is 16. Okay, so that's an ellipsoid, but notice all the coefficients are the same. That's a special kind of ellipsoid. Okay, that's an ellipsoid that goes, if we divide through by 16, it's going to go plus or minus 4 in the x, plus or minus 4 in the y, plus or minus 4 in the z. That is a sphere. Okay, it's going to be a sphere of radius 4. So that's I. And next up here we've got, let's see, we've got one negative on the left hand side, two positives. We need to bring this over as a positive 16. Okay, and if we divide this off, if we divide that 16 off, then we're going to have a 1 on the right hand side. Okay, so these guys cancel. We get a positive 1 on the right hand side. We've got positive x and a positive z and a negative y. So two positives and a negative with a 1 on the right hand side. So positive 1 on the right hand side, two positive terms here and a negative. So this one went along the z-axis because it was negative z coordinate, hyperboloid of 1 sheet. So this will be hyperboloid of 1 sheet, but it'll go along the y-axis. So that's B. Just along the y-axis. X squared minus z equals 1. If we solve that for z, bring the z over here and the 1 over there is a negative, that's going to be z equals x squared minus 1. So z equals x squared would be a parabola in 2 dimensions, shifted down 1 unit, but now y is left out, so it's actually going to be a parabolic sheet, or what they call a cylindrical surface. That is G here, a cylindrical surface that's not a cylinder. Cylinders would be like x squared plus z squared equals 1. Or x squared plus y squared equals 1. Okay, so that's G. And then let's see here, we've got a positive y squared, positive x squared equals 9. Z is left out here. We could divide the 36 off on both sides, and we'll see that this is another cylindrical surface, and this one's an elliptic cylinder. It's not a circular cylinder, but it is a cylinder. and that is A. So if you divide 36 off here, or I'm sorry, not 36, 9, because we want a 1 there to be standard form. Okay, so then we've got a 4y squared plus x squared over 9 equals 1. We'd have to take the 4 down on the bottom as a 1/4. And we'd see that, you know, the radii here are different. This one will have a 3 squared on the bottom. This will have a 1/2 squared on the bottom. So it's elliptic as opposed to a circular cylinder. And then our last one, we've got y to the first power, x and z are squared. So we're looking for something with one variable to the first power here and here, and the other are squared. These two are positive, that's paraboloid. One positive, one negative is a saddle, or hyperbolic paraboloid. So we've got two positives here. This minus flips it over, so that's flip over the, let's see, this is y in terms of x and z. So that's going to be a paraboloid that opens like this along the y, but then the negative sign is going to flip it so it opens along the negative y. And then this plus 4 is going to shift it 4 units along the positive y-axis. So this is going to be a flip over the xz plane. Okay, yeah, the xz plane, which is the plane y equals 0, because it's along the y-axis. But that is an elliptic paraboloid here, which is C. And so the one that didn't get used was a hyperbolic paraboloid, the saddle. So this is just nice exercise in getting you to identify some of the standard forms there, recognize them, but not have all the work of having to graph everything with traces. Okay, so now we're actually going to do some sketching here. So we want to take this surface here, and we first want to put the equation in standard form. I notice two positives and a negative. I bring that 16 over. Two positives and negative and a positive 1 on the right hand side. This is looking like a hyperboloid of one sheet here. Okay, it's looking like this. This is a negative z, so along the z-axis this is a negative z. So it looks like a hyperboloid of one sheet along the z-axis. So well, let's take and put it in standard form. So plus y squared minus 16z squared. Let's add 16 on both sides, so this comes over as a positive 16. We want to have a 1 on the right hand side, so divide through by 16. Whoops, that's a y squared. And so we get a 1 on our right hand side. These guys cancel. Got a negative z squared there. And then this is going to be y squared over 16, or 4 squared if you want. 4 cancels into 16 4 times, so x squared over 4. So there's our standard form, and this is a hyperboloid of one sheet. And it's along the axis with the negative coefficient, so it's going to be along the z-axis. So if we go back here to our reference sheet, we can see what the intercepts are going to be. So, this is, yeah, so plus or minus a and plus or minus b. So those are the coefficients under x and y. Those are going to be your intercepts. So intercepts here, let's go ahead and do those guys first. So if x and y equals 0 here, then both of these terms drop out, and you get negative z squared is 1. So that has no solution. So there's no z-intercept, which makes sense. And then the plus or minus 2 and plus or minus 4 are the other intercepts. So if x equals z equals 0, that's going to be y-intercepts. So that makes this term and this term drop out. So you get your y squared over 16 equals 1. So y squared equals 16. And y equals plus or minus 4. So that's your plus or minus b. And similarly, if y equals z equals 0, that's going to give you x is plus or minus 2. So we can start to do some sketching here of the graph. So y-axis here, x down here, z up here. Go ahead and start marking off here. And I'm keeping equal scaling on my axes here. Units of 1. So y plus or minus 4. So that's going to be out here at positive 4. And then down here at negative 4. X plus or minus 2. So positive 2 would be right here. And negative 2 is right there. So those are our intercepts. And we want to see at least one trace in each direction. So let's look at some traces here. So we know it's a hyperboloid of one sheet that comes along the z-axis. So we know it looks something like this. Okay. We know, rough sketch, that's what it looks like. Okay, but we want to get those traces in there to get a little bit better idea. So first let's take the trace z equals 0. So if you plug z equals 0 up here, then you get x squared over 4 plus y squared over 16 equals 1, which is an ellipse. And in fact, that's the ellipse that has these 4 intercepts. So you're getting this ellipse that's longer than it is wide. Okay, so that is z equals 0. And let's do another trace. Why don't we keep up with coordinate planes? They give the nicest traces here. So what if x equals 0? Then that's going to drop out this term. So you're going to get y squared over 16 minus z squared equals 1. And that's a hyperbola. And that's actually z squared over 1. So remember, this is y squared over 4 squared and z squared over 1 squared. So this is a hyperbola that opens along the y-axis. And to sketch that hyperbola, remember what you do, and this is in the yz plane, so that's in this plane here. Remember what you do is you make a rectangle that goes plus or minus 4 in the y direction. And that 4 is square root of 16, and then plus or minus 1 in the z direction. And you sketch a rectangle in there. And then you put asymptotes through the diagonals of that rectangle here. So I'm going to use my line tool here. Get some asymptotes in here. Okay, so there's one asymptote. And we got another one comes like this. About like that. Okay, so let me see. Let me do this trace and red. Okay, so x equals 0 is going to be in red. So this guy comes in like this. It's asymptotic to those. So this is pretty steep parabola. So it looks something like this. And then same thing on this side. Okay, not too bad. So this hyperboloid is really squashed down. It opens really wide. Okay, let's do one more trace here. Let's look at y equals 0. And if you drop out the y equals 0 term, we get x squared. As if you plug in y equals 0, this term drops out. So we get x squared over 4 minus z squared equals 1. And again, that's z squared over 1. So you go plus or minus 2 in the x, plus or minus 1 in the z. So plus or minus 2 in the x, that's here. And then plus or minus 1 in the z, so that gives you a rectangle to draw the asymptotes through. Okay, so I'm going to sketch these guys again. So something like that. Okay, and that's in the XZ plane here. And then another one going through about right here, down to back there. Approximately right there. Okay, and let me sketch this trace in blue here. So here is the intersection point. Oh, again, this is another hyperbola. So it's got a vertex here and a vertex back here. And that opens wide, but not as wide. So like this. And then in the back, like this. Okay, so then, it probably wouldn't be a bad idea to do one more trace in the z direction, like, maybe up at height z equals 1, to get an idea of how much wider this circle goes out. So why don't we do that real quick. So z equals 1. If we plug that in here, we're going to get this same ellipse, but then -1 here is going to come over as a +1. So let's go ahead and write that. So x squared over 4 plus y squared over 16 minus 1 equals 1. So bring this over as a positive. This will be a 2 on the right hand side. And then we need to divide everything by 2. So then that's going to be x squared over 8 plus y squared over 32 equals 2 divided by 2, which is 1. So then our our vertices on the two axes of the ellipse here are going to be at plus or minus square root of 8, because that's square root of 8 squared. And then your 32 is really square root of 32 squared. Okay, so square root of 8 is between 2 and 3. So if we go up to height 1, we're going to come out somewhere between 2 and 3. And so it looks like we're going to have a point about there. And here we go up to height 1, we're going to come out between 2 and 3, and probably point somewhere about there. And then in the y direction, we go out to square root of 32. So 5 squared is 25, 6 squared is 36. It's a little bit closer to 6. So it's 5 point something. So we're up at height 1. We're going to go out to almost 6. So that's probably going to be about right there. And then same thing over here. So I go out almost to 6, and then we're at height 1, so about right there. So now I've got 4 points to draw this ellipse through. And then we're going to have another one like this that's down low. Okay, so we're going to have another one that's at z equals -1 that goes through the underside of this guy here. So and this guy curves in here, and it curves in here. So that's a really flattened hyperboloid of one sheet. So I'm going to try and do something that's not, too terribly hard to draw. Saddles are kind of tough. So I'll try and be reasonable. Just want to see that you understand traces and can identify. All right, let's see. Next up, we're finding some arc length. The arc length of a helix here, t, 3 sine t, 3 cosine t. So 3 sine t, 3 cosine t in our y and z, that forms a cylinder along the x-axis, because x equals t is what is varying there. Here, it's only a portion of the helix from 0 to pi over 2. But we want here to use our arc length formula, which is integral from a to b, and then we're square root of the sum of the squares of the derivatives. So it's going to be dx dt squared plus dy dt squared plus dz dt squared. So that's our arc length element. And then with respect to t. So we are integrating from 0 to pi over 2. And we got a square root in here. Dx dt, x is equal to t, so dx dt is 1, and that gets squared. Y is 3 sine t, so dy dt is going to be 3 cosine t, and that gets squared. And then z is 3 cosine t, so dz dt is going to be, derivative of cosine is negative sine, so this will be a negative 3 sine t, and that guy gets squared. And if you square these, here you'll get 9 cosine squared t, plus here you'll get 9 sine squared t. And you can factor that 9 out, and you'll have cosine squared t plus sine squared t, and this is equal to 1. So we've got a 1 here, and we've got 9 times 1 here, so we really just got 10 underneath the square root sign. So this is really just the integral from 0 to pi over 2 of square root of 10 dt. You integrate a constant, you just get constant times t, so this is root 10 t, and we're going from 0 to pi over 2. So plug in pi over 2, plug in 0, and subtract. So this is root 10 times pi over 2 minus 0, which is just going to be root 10 pi over 2. So there's our arc length. I'm going to try not to do anything that's too crazy here. If I give you an arc length formula, some alternatives in here for applications. Remember, this was one of the applications. So some alternatives for applications that you should review would be work problems. We did one in the homework, also in the notes. Tension problems, where you look at components. Did one in the notes, one in the homework. Projections, we did projection of V onto U, but then remember I also mentioned projections that were parallel and perpendicular. Another application we saw was the volume of the parallelepiped that was determined by vectors A, B, and C. That was the triple scalar product. Then also angles between vectors and angles between planes. Those are both related. Remember, the angle between planes is given by the angle between the normal vectors. And alternative line problems, we checked for skew lines. So that's another possibility to swap out for the line problems. And then we did examples of parameterizing a curve in terms of S, in terms of arc length. That was leading into finding t and then also n, the normal vector to a curve. So those are all things that you'll want to review. So this, this review, it gives you a good idea of, in general, what to expect on the test, but it's not exhaustive. So you do want to go ahead and review some of these other topics. But we go over most of the basics. We got about 75% of it here. All right, so last problem here. We're given a position function for a particle, and we want to describe the motion of the particle for t equals 0 to infinity. So in particular, we want to find velocity, acceleration, we want to find the unit tangent vector, and then also the curvature. Okay, so v of t is just r prime of t. Remember, speed is the length of the velocity vector, or the length of r prime. So remember, what we do here is we just differentiate each component. So if you differentiate a t, you get 1. Derivative of 1 is 0, and your derivative of t cubed is 3t squared. We also need acceleration. So acceleration at time t for this particle is just going to be the second derivative. So that's just going to be r double prime of t. So you differentiate 1, you get 0. Differentiate 0, you get 0. And derivative of 3t squared is 6t. Okay, and then we're going to need to find that tangent vector, which is r prime over the length of r prime. So we need the length of r prime in here, which is actually going to be the speed. Parenthetically. And so the length of r prime is sum of the squares of the components. So square r1, and we got a 1. And square the 0, we don't get anything there, and then square our 3t squared. So this is just going to be square root of 1 plus square the 3, we get 9, square our t squared, t to the 4th. So there's our length of r prime. And then t, our unit tangent vector. Remember that r prime, the velocity vector, is a tangent vector to the curve. The unit tangent vector is r prime of t divided by its length. So our r prime of t is here. So we got 1, 0, 3t squared, and then we're dividing by root 1 plus 9t to the 4th. And then, let's see, last thing we're finding is curvature kappa. So remember that kappa at time t is, our shortcut is that this is the length of r prime cross r double prime divided by the length of r prime cubed. Okay, so this is length of r prime of t cross r double prime of t, and then we divide by length of r prime of t cubed. That's the easiest formula. Okay, and now let's find this to fill in. We already know this. Okay, that's right here, so we'll just have to cube that on the bottom. So let's find r prime of t, and let's cross that with r double prime. So that's going to be a determinant with I, j, k in the first row. And let's see, r prime goes in the second row, 1, 0, 3t squared. And then r double prime, 0, 0, 6t goes in that third row. And multiply these cofactors out. So take out the row and column for I. So we've got 0, 3t squared, and 0, 6t. That gets multiplied by I. The j term gets minus, and we take out row and column for j, so 1, 3t squared, 0, 6t. And times j, and then plus the k cofactor, take out row and column of k, 1, 0, 0, 0. Alright, so let's see, cross product here, both of them are 0, so that's just going to give us a 0i minus 6t minus 0, so 6t j, and then 0 minus 0, so 0k. So if we write that in component form, that's just 0, negative 6, 0. Then the length of this vector is just going to be square root of 0 squared plus negative 6 squared plus 0 squared plus not equals, which is just square root of 36, which is 6. So this length up here is 6. Let's see here. Oh, I'm sorry, 6t. This is a negative 6t. and this will be a 6t. That gets squared. So that gives 36t squared, and then take the square root, you're going to get 6t as long as t is positive. And okay, we're not given values of t here, so this is going to be 6t for t greater than 0. So for right now, we'd have to be assuming that t is greater than 0. If not, then we just have to leave it as square root of 36t squared. That is, square this and just leave it under the square root. Okay, which is what we have to do in this case because we're not given any domains, so we need to assume that it's minus infinity to infinity. So that's what goes up on top right here. So square root of 36t squared. And then down on the bottom goes our root 1 plus 9t to the fourth, and then that gets cubed. And we really don't need to do any simplifying there. I mean, you could, if you wanted to, you could make this a 3/2 power. Yeah, actually, you could take the 6 out. That'd be okay. So you'd have 6 times the square root of t squared. Okay, which can end up being positive or negative t. So that gives us kappa. Let's see, part B. We want to find a normal plane at the point 0, 1, 0. Notice that 0, 1, 0, if you equate the x coordinates, that implies that t equals 0. So in part B, we want the normal plane. So our point, we need a point in normal vector. Our point we've already got, 0, 1, and 0. And then the normal plane. So remember, with the normal plane, your normal vector this is normal plane to the curve. So your normal vector for that plane is equal to you can use the unit tangent vector, or you can use r prime, whichever is easier. And so for us, r prime is going to be a little bit easier to use. That's right here. Okay, because our unit tangent vector, we've divided out that length, just makes it more complicated. So for us, that's 1, 0, and 3t squared. And then at the point 0, 1, 0, t equals 0. So t equals 0 gives us 1, 0, and 3 times 0 is 0. Okay, so there's our ABC. So now we just have to plug into the scalar equation of the plane. A times x minus x0 plus b times y minus y0 and c times z minus z0 equals 0. So a is 1, b is 0, c is 0, and x minus 0. And then this is y minus 1, and then z minus 0 equals 0. So this term drops out, and this term drops out. So we've essentially got 1x equals 0. So this is x equals 0. is our normal plane. So that's the YZ plane. Okay, part C asks, is the particle ever at rest? It's going to be at rest when velocity is equal to 0. So this is asking, is velocity ever equal to 0? Well, our velocity is 103t squared, so you'd set 103t squared equal to the 0 vector. So it'd have to be 0 in every coordinate. And this coordinate's always 0. This coordinate is 0 when t equals 0, but the first coordinate is never equal to 0. Okay, because this is the vector 0, 0, 0. Okay, and 1 is not equal to 0. Or if you want to look at speed, which was the length of r prime right there, so your speed equals square root of 1 plus 9t to the 4th. And if it's at rest, you set this equals 0, and there would be a solution, but there's not. So the answer is no, it's never at rest. Then let's see, next up, what happens to kappa as t approaches infinity, and what does that mean geometrically? Okay, so part D, going back to our curvature, which is right here. So we're looking at the limit as t goes to infinity of this expression. So root 36t squared over square root 1 plus 9t to the 4th cubed. And by looking at dominant terms, this is the limit as t goes to infinity. And upstairs, this is going to be, t's going to positive infinity now, so we can take square roots. So this will be a 6t on top. And then the dominant term on the bottom is going to be the 9t to the 4th cubed square root. So square root of 9t to the 4th cubed, which is the limit as t goes to infinity. 6t over this square root of 9 is 3, square root of t to the 4th is t squared, so 3t squared cubed. So this is going to be a power to a power, so it's going to be a t to the 6th on the bottom, which is going to go up a lot faster than t on the top. But if we want to take the algebra out one more step here, t goes to infinity, we've got a 6t on the top, cube to 3 is a 27, t to the 6th on the bottom, and then this t will cancel off one of those, so the top is fixed, the bottom goes to infinity, this limit is 0. So kappa approaches 0. And what does that mean geometrically? That means that the curve gets flatter. Okay, it gets flatter and flatter. Yeah, fatter, no, flatter. And then part E. Use your calculator to sketch the graph for kappa and estimate where the curve is tightest for the R of t in part A. Okay, so in other words, this curve right here, where is that curve? At what point or what t value is that curve tightest? Oh, you know what? Here, I'm sorry. We're describing particle motion here for t between 0 and infinity. So we actually could have simplified this to be 6t here, and we could have used the 6t right here. Okay, so that would have been fine. Yeah, so here we could use the 6t right there. Sorry, didn't notice that. Alright, so if you graph this on your calculator, so you just want to enter in the kappa function here. So this you can just use 6t. And then the bottom we've got to leave. So 1 plus 9t to the 4th. And then whole thing cubed. And if you graph that, you get these two bumps, get two maximums. It goes down at t equals 0, the top is equal to 0, so the curvature would be 0, so the curve flattens out. So it comes down here and hits 0, and then it comes back up, and has this other bump, and then it tapers off to 0 here, and tapers off to 0 here. And you can estimate on your calculator, if we just estimate to the nearest tenth. These turn out to be 0.4 and negative 0.4, and it's a symmetric curve. And those are really the critical numbers of this function. So if you found kappa prime of t and you set it equal to 0, that would be at t equals 0, and then you also get them at plus and minus 0.4. And then you can just plug in those values into the equation of r of t and get the points. So if t equals 0.4, then your r of 0.4 is approximately, it's t in the first coordinate, so 0.4, and then 1 in the second coordinate, and then in the third coordinate, so let's see, it's t1, and then, yeah, t cubed. So 0.4 cubed, which is 0.064. And then at t equals negative 0.4, do the same thing. So you'll get negative 0.4, 1, and then negative 0.4 cubed is negative 0.064. Okay, so these are the 2 points here where the curve is tightest. Okay, and then this point where kappa hits 0, so this is kappa here on the y-axis versus t on the horizontal, is where the curve flattens out near t equals 0, and then flattens out at plus and minus infinity. So, okay. So, let's see. Other things I could ask you with curve. I'm probably not going to do binormal vector here because it gets awful complicated. I have to give you a really, really easy function to do anything with binormal because you have to take a derivative of your unit tangent vector, which is this guy right here, and that involves using the product rule with this scalar function times the vector, and that usually turns out pretty messy. So unless the length ends up being constant all the time, like a circle or something like that, probably not going to be looking at the binormal vector. Which means probably not going to be looking at the binormal plane here. All right, I think that's about a wrap.